There are another systems which many of the broadband or communication people use, which is called telemetry tracking and communications. If you have multi-channel data coming in and you have multiple receivers, multiple transmitters. So if you see a system which is shown here, which need not be actually understood fully, just to show you that there is a committee which says consultative committee for space data system, which decides much of the data, like FCC standard decides for communication. The digital part with mixed signal is decided by so called CCSDS people. So based on this you can see there are many divide by 2 or something, but there are some kind of a mixers, there are IF down means that means there is amplifiers, and these are filters. So obviously if you look at these systems, one of the problem one sees, since the data is coming at different clock rates and the system has to go through a single receiver per se, in that case they have to be synchronized with a clock. The data may be coming at any other clock, but they have to be synchronized. So there is a what is called TTCRX for a receiver. So basically if you see a recovery data for that for a given clock, then there is a low noise amplifier followed by PLL, and that will allow to clock all data coming out at a given clock. And there is a skew function which is equivalently called jitter. So you can minimize jitter by finding how much tap delay one should use. The basic idea there is you actually delay each channel by a given say 0.1 nanosecond and then pick up the data serially, so that everyone is synchronized with one clock cycles, and this requires at least 2 of the most famous analog blocks, the low noise amplifier and the PLL. RF as such is an independent area, but since its method of design is almost same as what we do in the case of analog, so RF CMOS is also considered as analog CMOS. The problem right now is the cost. Since the cost of a chip, mixed signal chip, is decided by the microprocessor people or the digital hardware people, since the microprocessor is very cheap, so is the memories are downright cheaps. A 256 MB DRAM may be sold in few dollars or few rupees now, and because of that, the technology being so advanced, people found out that the bipolar technology, though has advanced compared to what I did in 70s and now what people are doing in CMOS, still much costlier. But I repeatedly telling you why bipolar IC I am talking. If you are only looking for analog market, bipolar or bi-CMOS or bi-MOS technologies are still the ideal technologies as far as performance goes. But there will be very few independent analog blocks like op-amps or something, whereas most of them will be mixed signal, and in that case the CMOS will rule. And if CMOS is to rule, which is going to say 11 nanometer down now as a new technology node, we are already working on 16, some chips have come, 22 is already marketed, and 11, 7, maybe 0, I do not know. So if that scale down comes by Moore's law, so the cost will keep on going down simply because the number of components you can put on a chip will be so high, so digital will govern the market. So the problem started with RF is that you have to compete with those people, or you have to compete with that technology which is not so very good for RF. Now if you see all the submicron devices, all of them are looking for low power. The word itself suggests RF, which has a power amplifier built in there, you will see someday. The word itself is power, okay. And then we say, like last year one of your senior colleague of dual degree, I asked him to design a low power amplifier. So the first answer he said, what are you talking? I say, yeah, that's the fun. The power delivered is called power amplifier, but power consumed by the device and the circuit is essentially the power lost. So I am looking for low power amplifier, okay. So I may require 10 DDM power outputs, but I may require much less power dissipation in my chip, okay. So that is the challenge right now one is facing, that you are working on a technology which is going for low power and low power, but RF does not want that, okay. So yeah, I mean if CMOS can do it, it will, and that is what is going on. So whether we like or we do not like, CMOS is going to stick. Here is a typical mobile phone architecture. This is your antenna, this part is receiver part, this part is the transmitter part. If you see it, there is a filter, image reject filter. Essentially it occurs because of the way you actually receive the signal and pass through a amplifier. There is a band which will reflect by Fourier transform. So you will see an image somewhere else, and if that image comes closer, it acts as a noise when reflects. Okay. So you need extremely low noise amplifier, which is shown here, followed by a filter which will remove those images, followed by a mixer, another filter for lower frequency which is called baseband 400 megahertz or sometimes 200 megahertz basebands, amplifiers, and then again you have 4, because you work normally on quadratures, so you need 90-degree offs. So this is baseband 1 and I and Q, and this is the 2 mixers, 2 low pass filters. Similarly for the transmitter side, you can see there are filters, IF level controllers, single sideband mixers, buffers, power amplifiers, and there is of course frequency synthesizers which are like PLLs. So if you look at the typical RF kind of part in the mobile, this is typically what is the mobile part. Once you are in a baseband, all digital signal processing will start, and you will have A to D converters and then everything digital. So the why we wanted to actually put all this IF down, because otherwise the requirement for conversion of ADC using ADC will be huge capacitors. One of the important thing of VLSI is the area. We are looking for as small an area for the circuit as much as possible, so that more and more chips can be created from the same silicon area. So because of that, one has to see here that majority part processing will be digital, and mostly now, as I say, below 45, and this so called RF part has to work on 45, which is the biggest challenge all analog RF people are facing. If you allow me to work on 0.25 microns, 0.35 microns, I assure you that my performance will be best possible. Whatever any GSM or CDMA or any of the other iPads or iPods wants, we can give far better performance, or if you do on bipolar it is even better, but that it will heat so much that you will have to cool it by putting somewhere, so maybe fan is required, so the bulk will go. So in some sense, bad tools and you won't expect a good product. Similarly, if you look at the typical for integrated services for telephones, which has telex, fax, data, everything in one, which is a comparatively higher frequency than normal, and but you can also see there is a oversample D2A, a pulse generator, a low pass filter, line driver which is an amplifier, there is a filter here, there is a gain control amplifier, a tone detector. So all of them, if you see, once you are in XFR, that is you can go for digital, but earlier to that the front end everywhere is analog. So our design criteria is that you should be able to interface digital part and achieve the best performance on the analog or RF part. That is the challenge which everyone faces. Just to give a simple circuit of a bipolar RF FM transmitter and FM receivers, I suppose some other course some other people will teach you, but this course may not. Modern communication system like mobile communication, LANs, GPS system examples, and as I just now said, trade-offs are between design and the other parts. In compared to digital, where I do not know whether you have, some of you might have already done a digital course or digital design course or maybe now doing it, the 3 criteria we put for a good digital design on a chip. We say okay, it should have a low power, it should work as high speed as possible, so the delay is minimum, and third we say okay, it should have a smaller area, so it is called triangle. We only optimize between area, power and speed, so this is the triangle. And you can see if a given triangle is fixed for a given technology, if you reduce power, obviously something else has to be increased by triangle stretching, and that means you will have to compensate by either by reducing speeds or giving more area, okay, which does not fit into requirements of normal good digital hardware, and that is the challenge there. But in case of RF or analog, the design is not only 3 cornered, it is a multi-cornered discipline. For example, a typical design requires a lot of theory of communication. You may get random signals, you may have different transceiver architectures, homodyne, heterodynes. You are required to do a good IC design, all criteria you have to fit in. You need a lot of CAD tools, you need wireless standards to meet, you have multiple access systems, LMDS and many other points, and you have to know about signal propagation. So if you see the disciplines required, we figure out this is the way you will have to optimize. You have gain, frequency, power, noise, linearity and supply. There were 3 in the digital, and now you can see at least there are at least 6, maybe sometimes 7, we will come to it later. So the optimization is not trivial in the case of analog or RF designs, and that is the reason why analog becomes more challenging, or more requirement from a human intervention is much more in case of analog than in case of, if you know as a IBM process, you know the typical process has been used. IBM has a very strong good wireless process, CMOS process, which has been used in Bluetooth, WLAN, set-top box transceivers. Mumbai, Delhi, Chennai, of course compulsorily you should have set-top box now. Hopefully it is good for us because it gives so much money. IF and baseband part of all radios will require all CMOS wireless. So what are the challenges for CMOS? I said it, I repeat. The different performance requirement for analog and digital. Analog requires something else, digital requires something else. So now you are on a single chip, you are fighting each other. CMOS technology is always optimized for low power, but often it gives the worst performance for analog. So now again you are fighting for it. The smaller the device you make, better is digital performance. That is what we are looking for. Why we are scaling down? Because we know performance will improve great. The simple reason is the time taken for electron or hole to go from source to drain will be smaller as the channel length goes down, and if the time is smaller, obviously speed is higher. Okay. Data can proceed faster. Whereas in the case of analog, the short channel effects which digital is facing is even worse for us, because then everything which I thought as no noise around, they all will act as a noise to my inputs, and my worry starts that how do I get rid of these noise parts. Okay. Since we are scaling down VDD for all technologies, we went from 5 volt, 3.3 volt, 2.1 volt, 1.5 volt, 1.2 volt, 1 volt, 0.8 volt. Now we are looking for 0.6, maybe some chips are already there on 0.6, and I do not know, 0.4 may be the last, I hope so, because then the noise 1 kT by Q is 25 millivolts, it is room temperature, 4 kT is the normal thermal noise around, so 100 millivolt is the noise. So if you have a 400 millivolt power supply, VT has to be around 0.1 100 millivolt, so you are in a noise zone. Okay. So one does not know which device will be switched off or switched on, God will tell. So that cannot happen. So some way probably 0.4, of course as whatever I say today is qualifiable 5 years down. Some 10 years ago something I said, or 20 years, is all proved false. So what I am saying may not be true in future, but maybe I will not be around to compete for you. Okay. As you scale down, there is a transistor mismatch, because the two transistors even close by, one cannot guarantee their same thresholds, same W by Ls or same mobilities, and if you can on a chip there are so many, it is impossible to match everywhere. This is called variability issue. Some of my students have worked on it, and that is creating a huge design issue, because if there is a variability, how do you design a chip? Some part may work sometimes, some part may not work sometimes. So how do you actually figure out that how do you get the maximum output even if there is a variability? So there is an issue which is very important of 2005 onwards. I already said that analog functions only work very small input range, and though I showed you a linear curve there, but if you see at the edges, and in reality even that the line which I draw is a straight line is only because I wanted to draw it straight line. In real life it is not a straight line. Okay. It has some finite slopes there, and it changes as you go down in Vns, though we assume dV0 by dV is constant. It is good for us to solve, okay. But in reality nonlinearities exist, and if that exists, analog functions will give you different gains, different noise, everything different bandwidths, and there is an issue involved. There is another problem which analog is getting, because you are working on a same substrate for analog and digital. Digital switches 10 10 10. Now the substrate bias also keeps changing. Any bias change will shift my Vt, and my Vt shift means my everything analog gone. So I must separate, because otherwise I have an issue that anything I on digital is reflected in every analog outputs. Okay, there is a noise sitting immediately. Now apart from substrate noise, there is always what we call flicker noise, variation noise. We will come to it later in the course itself, which is called 1 upon f noise. So lower the frequency you operate, higher is the noise. All said and done, after certain frequency, once say thermal noise takes over, we shall show that. But generally lower frequencies the flicker comes. But lower does not mean it is 0 or something, it gives some few hertz to few kilohertz or few nowadays even few megahertz, because cutoff is going as much as megahertz. So because of that the flicker is varying extremely, and as you scale down technologies, the variations in mobility in particular due to interface state variations is very high, and because of that the flicker is very high. So one of the worries which all mixed signal people are worried about is the flicker noise. So called non-quasi-static effects, those who are device people who have learned devices course from me, hopefully we keep telling all the analysis this is steady state or thermal equilibrium. Okay. In real life there is nothing called steady state, okay, it is non-quasi states, and since it is non-quasi steady states, there are huge problems in modeling, and if you do not correctly model at those RF frequencies of gigahertz and above, you have more problems in design, because what you thought correct is not at all correct, and then the design will show even more problem for its own, and then the chip will never work to the specs you are looking, or may not even work. Okay. So that is the major worry of a designer in mixed signal area. Digital design, so many CAD tools, Synopsys, Cadence, Mentor Graphic, you name one, there are strong CAD tool companies which have provided tools to the as lower technology as say 16 nanometer tools. In the case of analog, there are no such easy tools available. Okay. Each chip is a different requirements and different issues come. So one does not have enough CAD tools even in 2012 that you can use those tools. Some tools of digital can be transformed on analog, like for Cadence layout tools, yes you may use them here. But Cadence has a problem that unless you use a analog layouts areas, what it shows that two lines cannot be separated by certain, there is what is called design rules. These may be very stringent for digital, but analog we do not need those stringency. I can actually separate anything, okay, because my area is enough for me. But I will be forced to do that, because otherwise that tool will shout and will not allow you to put a layout also. Okay. So they need to be modified for analog function performances. The problem with all this is that design time is very high in analog per unit area, maybe total it may not be as high, but per unit area design time is much higher in analog than in digital. The layouts are what almost when we say handcrafted. Handcraft means by as if you are drawing by hand. Tools will give you line drawings and all that, but you will have to decide, should I put it here, should I put it there. So decision is mostly yours and not tools. In digital, you say I want an AND gate, it will replicate without you asking it also, okay. It will show you layout for that, okay. Because there is a library which actually stores most of it, okay. Such facilities are not available for any analog blocks, which we are trying, that is our ultimate aim. People say IP creation, someone other day asked IP stands for intellectual property. If I design it something, got fabbed and tested, that belongs to me, and I can sell that technology or that block as an IP to anyone who wants to use that. Okay. So one of the major activity in analog right now is IP creations. So you create some hundreds and thousands of IPs, someone will buy hopefully and then use it for you and give you some money as well. The analog part costs approximately 2.5 times that of digital. For example, 0.18 micron, the cost is 2.5 times 0.35. So if you go to 45, you can think of it how much cost I am unnecessarily putting on. I know the performance is much better at 0.35. I am scaling down and pushing myself to put more money on it for no good reason. I am getting worse performance, paying higher. Okay. Yeah, you have a point. Most of the analog GM part, which is decided by transconductance is proportional to lengths or root lengths. So larger the length of the channel, larger will be GMs. Is that correct? That is our major criteria. GM should be as high as possible, gain GMR, okay, GMR 0. So if I want higher GMs, I should have a longer lengths. Okay. In digital, I will prefer to have shorter length as much as possible to improve the speed performance. Okay. So in some sense, I know my 0.35 will be better, but I am working on 0.45 or 0.045 or below, and now I am asking that performance be as good as what you could have given in 0.35. Okay. So that is our major issue. Okay, I will come to it anyway, that is the course. Why analog I already said. Okay. And you pay higher, and the worst is getting worse results and you pay higher, inversely proportional. This is the typical SOI, silicon on insulator substrate. You can see the two parts which are shown here, one is digital block and analog block, and through substrate there is a connection. Okay. This is called substrate couples. Now some other additional hardware or additional processing has to be done, which is called guard ring technology. Some guard rings can be pillar kinds, okay, so you have to put pillars down as much as below, so huge cost on that. But if you do that, digital could be possibly separated from analog to some extent, and therefore the noise coupling may be smaller. This technology is costlier. As soon as you go on silicon insulators, the technology is at least 4 times costlier than normal silicon bulk CMOS. So cost. Here are just quick photographs. This is taken from Texas Instruments. He is Texas Senior Fellow of Texas, Bill Witowski. We have called him some years ago, and that is his talk which has been copied here for you. One of the major activity in the RF area is broadband, which is network shown here. There is a gateway packet network transmission, then there is a premier access gateway, and so many equipments can be connected: laptop, video camera, iPads, iPods, mobiles and desktops, all are connected through broadband. There are drivers of broadband. Why so much looking? Because internet is becoming part of your life, and if you want to have video streaming, audio of course is not that difficult, but if you have a JPEG going on it, then you have too many standards on MPEG, JPEG together, and you need huge hardware improvements. So that is why broadband is very important for most cases. I think these are available, mostly you know about. The major worry is what we call quality of service. All communication people must be happy I am talking their language. One of the major worry in all transmissions is quality of service, how services are provided to you. When you reach home, from home to your whatever called hub, do you go on which fiber, do you go on fiber, or you are on wireless, or you are on copper, all these may decide quality of service. Okay. For example, the evolving network home meets lifestyle, because you are so much busy with working outside, so you want almost everything automated, home automation including washing machine, fridge. So from a distance you should say, okay, switch off the machine or switch on. Rice cooker may start at 12:45, one close at 1, can do that. You need connectivity for all mobiles as well as pads, iPads and whatnot. You need to have all kinds of instruments which entertains you, including television and other through dish TV or otherwise, and you may work it on a system in which some kind of productivity is required. You have printer or everything access inside a room or in the building. This is what the cable network works. Most of you have cables, so you need a cable modem so that all 4 services can be given from the same cable. We worked on 5 years on DOCSIS standard for cable modem, but finally that chip did not come through after a lot of money we spent. Okay. But just to idea that cable probably is one of the best, because it has the highest bandwidth, and you anyway receive your TV channel on that. You can receive all your data, you can receive all your videos, you can do everything on the cable itself. You need modem for that. So right now one is not so much cable modems are popular, because mostly satellite direct home is what people are looking into, but the best quality of service can be given through a cable. These are all video equipments which requires lot of skills, and many IPs can be created for variety of blocks shown here. And you can see from a digital still camera, we are looking into broadcast equipment, IPVPR, video surveillance. This is also one area which is very important these days. Everyone wants to know what others are doing. What he is doing is not interested, what others are doing, that is the surveillance. Okay. So this is a link which is available on fiber, then copper, on single fiber, multimode fibers, where this wavelength division multiplexing is the standard optical signal processing methods. So for these also, which may run as 100 gigabits per second kind of frequencies, I mean data rates. So one is looking into variety of structures, gigbits, Ethernet, Sonet, and many of them which are required. All of them will be requiring some design which requires analog RF, particularly broadband. As I say, broadband is fueled by consumer demand. Everyone wants a broadband home. Broadband access is evolving very high speeds, always on internet to the connected home. You want to, of course all of us, I am no exception. Of course some of you are exceptions, I know. If I send a mail, you send reply after 7 days, either by design or by not looking your own mailbox, okay, either way. Particularly TAs, if they are not done the job, they keep mum, because then if they reply they will have to say I haven't done. So they, as if the mail has gone somewhere into the black hole. Everyone knows that if the mail has not bounced, I know it has reached, you can never say that it has not reached. But he says no, I did not receive. So, ठीक है, human hai, this is good for all of us. Mobile has given this advantage that I am standing here and I say I am in Delhi. No one knows, but once that 4G, 3G starts, if the video comes on it, actually background will be seen, and you cannot say I am in Delhi, you are very much in Mumbai, next 5 minutes away from the place, but you are telling I am in Delhi, I cannot meet you. Okay. This advantage probably may go soon. Okay, so probably one is looking for what we call system on chip. Many activities of a analog digital can be put on a single area called system on chip, everything together, okay, individual chips but put on silicon. This is like the PCB becoming silicon, okay, so that is the SOC. If you see a typical neural architecture, there are some, you can see some of the inputs of them I have shown you. These are multipliers, then there is a output you require which is called neuron activation function, which is actually which need differential outputs, okay, so diffamps. So if even in the smallest part of a neural network neural process I showed, there are at least 11, only 2 layers I shown you, there are 11 multipliers and at least 6 diffamps required. So even for any kind of processing, the digital part is fine, but analog is very, very important. Neural, of course, as I say, mostly analog. This is how you can see there are multipliers, adders and neurons. Weight functions means actually you multiply, okay, synapses, this is the neural network, some other day, some other time. Typical analog multiplier is shown here. This is very famous circuit called Gilbert cell. It is a 2 diffam cell or rather 2 diffam put together looking like 3 diffams. This is the analog multiplier. This is generally current multiplier and that is the strength of it. Okay. This is a typical actual architecture of a 231 neural network architecture for a processor, which was designed by one of my students in way back maybe 1994 or 95. Okay. Therefore not referred because this is ours. Okay. So where is the ICs, analog ICs or systems going? Mostly now they are going into automotive guidance, robotics, remote sensing, and all of them require sensors. For example, you need a sensor for visual motion, which are very small, consume little power, work in real time. Like car is going and you want to see some collision this, or you want to check your tire pressure, or you want to check something, or you are connected to GPS. Now all this will be requiring that the energy, optical energy which you receive, irradiance, is very, very small, okay, that energy is very small and the processing has to be much more accurate. So the worry starts that how do you make processors which are a different time frame it will come, and it is not a fixed time that every nanosecond I can pick up a data, it may come in picosecond, it may come in nanosecond, it may come in milliseconds. So the processor has to have way of knowing which data is coming when. So mostly what we do is called asynchronous designs, which is not clocked to a given single, but at the end to processing you will require synchronizations. Okay. Whenever you do this, those are digital, of course everyone, signal processing everyone done, there is a anti-aliasing artifacts will be seen, so you will require a lot of DSP kind of approaches to improve that. Now this is what everyone has so far, so many years including us have said, that analog is costlier. Okay, so here is one slide which I took from after great difficulty, figured out that analog processing is actually economic compared to digital. So how is the comparison? Okay, here is the one. The comparison goes that if you see for the same complexity analog and same complexity digital, analog is cheaper. But what you do is you compare it to say Intel Pentium 4 or Athelion or Atrion kind of this with a RF amplifier. Oh, how much it is. So the comparison is not correct. So therefore they say that analog is very costly or RF is very costly. In fact, as I say, per block design if you see, analog will be cheaper. Because then that is how we can make a lot of pixel based system which can be addressed, very small pixel, I mean large number of pixels can be put in a smaller area. Okay. Can address very easily actually. The problem with all analog processing is it has a lack of precision. Digital you do not have real precision, 0 1 thoda idhar udhar ho gaya kuch nahi farak. So the problem is lack of precision, and but many of these, for example collision, if you have a collision detector, you do not want the car should be within 1 nanometer to know whether it will hit you or not. Okay. Even if it is a few centimeters, I know yeah I am hitting there or not. Okay. So many systems really do not require that precision either. Okay. So why are we fighting on saying, oh it is not precise? It is enough precise as far as the application goes. Okay. So these are issues. Why I am showing all this, all designers should get rid of this fact that what is the best design. There is nothing called best design. A design which works for a given application in a given money which someone buys is the best. Okay. If that does not meet either of the criteria, even if it has the best of specs, no one buys it, so what for it? Okay. So a design is as good as who pays and whether he is satisfied with the data output I am giving. If both are satisfied, thank you very much. Okay. So do not work on the best kind of designs, there is nothing called best. Okay. It is the best for an application for a person, okay, or for an user. If that meets whatever money it is, so what? Okay. If some specs is fantastic like space or someone asks you, you say okay pay $10 million for this chip. I mean he only 10 chips he wants, I have to design what specs are so horrible, yeah I will charge you. So that is the way designs goes. So do not get into this idea that, of course in exams we keep asking optimization, this is academic. In industry there is nothing academic, this you take from me now. There is a zero academics in industry. Many of these systems will require sensors which are motion sensors as they called. They are actually photoreceptors and they have to be processed on chip now. That is why this nano lab probably may help. Okay. Like in the case of MIT, I give you some university we are very famous. For example, MIT has been working for last 20 years or 15 years at least, I know, my good old friend Dr. Chandrakasan. They have been working mostly on vision area, okay, including eye and everything, all kinds of vision products. Basically signal for path of animal or machine, how to actually vision comes. So they are mostly working on bio analog or analog bio, whatever it is. The goal is to determine how the advantages of analog Vlsi, which is high speed, low power and small area, can be exploited, and as I said it has a limited accuracy, very inflexible, no memories. Of course I will show you some memories today if possible. It takes longer to design than normal digital and it takes hell of a time for debugging whether right or wrong. Testing is very difficult. So if you can minimize that, yeah this is a good challenge. One of the very famous book of 70s or 80s rather, I am sorry, It's come from Ismail and Faiz, which is now I am told available in India, earlier it was not. I have a copy, as I said I will not give. This person is still at Ohio University, and they work on the area of communication, RF CMOS, multimedia, instrumentation, sensors, medical and automotive. So why I am giving you show, so you also can think these are the areas in which analog VLSI is useful. A project 2010 they completed is the design of a CCD imager interface with CMOS chip with CDS, which is correlated double sampling. They also are designing AGCs, A to D converters for a camcorder. They have near term projects called chip design solution for multi-standard wireless, which is becoming very difficult right now. You have CDMA, TDMA, LAN, different kinds of LAN, different Ethernet connections, so you need different standards, and then you have to design a chip which meets 3-4 standards. Okay. The research spans in RF parts, LNAs, mixers, IQs, that is quadrature generations, and buffers. Baseband parts include channel select filters, variable gain amplifiers, high speed data converters, synthesizers, and design of low phase VCOs and PLLs. A very interesting memory has been, of course this is not from Ismail, a new memory has come now which is called floating gate analog memory. It is new in the sense actually it was known when I was maybe not I was studying after my maybe 70s. Analog was known to us earlier than digital, as I said you. So we knew about this so called analog memory then, but we could not think of that it will any time come, because in those days the flash was not made. So now we are using the flash digital memory what you call, and trying to see can we use the same technique or technology to create what we call analog memories. Okay. The basic analog memories is the storage of current of a constant current. So one current is 1 bit, the other current is other bit. Okay. So I can have a current mirror which has a constant current generator somewhere which stores that current. So that is what, and we use the same structure as E square PROM structure to do this, okay, from floating gate kind of memories. So this is a new memory which is probably is going to be used very soon, new flash. What is the advantage of current storage over voltage storage? Anyone? Why all these years we are actually looking for charge storage, isn't it? Q is CV, so V is the one which controls, there is no I in that, though we know very much I and Q are related, Q by T is I, but that T factor was very troublesome. Now we can manage that T, okay. So current storage is better, much more accurate, much more easy to create compared to digital, because larger the capacitance you create on silicon, huge area it picks up. So we want to reduce that area. So one possible way of doing, the only problem may come now, again we may have to look for current to voltage converters. So some op-amp based circuit will be required, because at then you may have a digital voltage data, okay. But these memories may come soon, maybe already they are made, so maybe another few years they will be marketed. Now before we quit on this, I must like to tell you many things about analog, because you all are analog IC market, strategic overview and opportunity. So I will just go into number of these points: market, characteristics, strategy and opportunity. Why opportunity? Because you may like to join. Okay. So what are the IC market drivers? As I said, driver means those who are pushing analog circuit designs. Automotive electronics, I said something about it already. Consumer electronics, energy, mobility, security, and the major right now everyone is looking is healthcare. Anything you put a bio on that, you are 10 levels up. So if you look at the market characteristics for analog, typically the market is decided by the money. So last 4 year dollar in billions we are talking about, and it is found that the improvement in analog technology or analog products is proportional to the other semiconductor technology products. So it is not that this is one area and that is one area, they are correlated. If that does not go up, this also does not go, okay. So it is very strong correlation functions. Typically we have found that 10% growth is seen in analog. This is cumulative aggregates which I am showing here, average this. Growth rate is from 2010 to 16, say $42 billion in 2010, which was 30% from the growth in 2009. In 2011 it became $45.2 billion, and we expect that in 2016 it will be $74 billion. The total silicon market is, as of now, is $800 billion. Okay. So we are not, at least 10% to 12% is something which we are actually working at. There are 5 famous companies in analog, some of them are in India, maybe all of them are in India also. So for example, very interesting, if I rank them, of course this is not given by the, I just taken different data and put it in a form for you to see. Texas Instruments is number 1 analog company in the world, which has the $6,190 million business in 2010, which has a market share of 14.6%. The ST, which is both based on France, Italy and US and also other European countries, it is ranked 2. They are more famous for their memories and other wireless products, but I am comparing analog part only. They are $4,291 million, which is 10%. Infineon, which has now become, part of it has become Intel Mobile, but remainder part of Infineon, which were earlier Siemens Semiconductors. Infineon is number 3 in analog market, $3,328 million business in 10, and it's around 8% share. Analog devices, they also work on a lot of DSP products, but their analog part is, they are ranked 4th, around $2,500 million business, 6% roughly their share. And one is very smaller company compared to these 4 is Maxim, which is 5th, which has around $2,000 million, which is only 5% of the business they do, but they do very niche business. The others make $24,000 million, which is 56%. But if you see the first 5 add, the 43% market share is really going to 5 companies. The remainder 100, there are 107 companies totally who actually work on analog. So the 56% with them and 5 sharing around 43%. And if you take it 10, then it will be 60% will be with them. Okay. There are a few bigger companies I did not list, Linear and others, but some other time. Okay. There are segments, there are 2 segments in digital, same is 2 segments in analog now, very strong segments. One is called application specific, the other is called general purpose. Like op-amp is a general purpose, kiske liye kya? Op-amp. Okay. So we say there are analog ICs that perform specific function like timing control, RF transceivers, touch sensors, LED drivers, LED coaters, display drivers. Then we have general purpose like multiple application like amplifier, DACs, ADCs, comparators, latches, all these sense amplifiers, all these are essentially general purpose, they do not go for a system. So if you look at their market in 2011, the application specific market is $26.3 billion. Now question is many times asked why I talk about billion. Firstly, I am copying from someone, so they talk in dollars. Secondly, we do not have even 1% of this business, so showing you some 22.6 crore business will be very odd. Then say why do I join that company? तुमको थोड़ा attraction देना है. 26 billion. The general purpose market is 18.8 billion. The main segment in 2016, the ASIC market will be 40 billion and the general purpose market will be 32. Typically $74 billion market will be in another 3 to 4 years of time. Okay. So what is the environment for them? Analog IC companies compete through what are their skills they require, they special product design skills. Each company has people who are expertise in one specific area, they can do this best, so they will actually use those skills. Then companies also compete on breadth of the product, how many products different kinds I create, that will decide my company's success. How much I am able to distribute and how good a network that company has will decide which will be 1 or 2 or 3. Okay. And of course finally, if not the, it's not the last, the most important, how much pricing you do for your products, that decides the environment for any company. So larger companies go by this, but if you look at the smaller companies, I have listed, of course these are not all from Canley, some are my own, I added there itself. So there is a small company in Korea, Asia led Trend, they only work on power management unit, okay, that is their only area, they do not work on any other chip. Richtech, they work on power management and LED drivers. Nico and Power Analog Micro, they work only on high voltage 20 volt, 50 volt power devices or power device based analog circuits. GMT works on audio switches, power management. Taiwan Semiconductor works on discretes, voltage regulators, op amps. Siltronics work only on LCD drivers. Silicon Metals work only on power management. So there are many others, I just didn't list all of them. So smaller companies actually choose a product or two and stick to that, because then they can create some niche market. Whereas bigger companies have other idea. They say larger the breadth, more you can make money. Okay, so that's the difference between the two kinds of market. Everyone survives, don't worry. Okay. Why I said you a few lines, then you will see it. Audio, video, clock timing, data conversion. For example, simple, I give one example. In 2010, ADC DAC market has 3.8 billion only on ADC DAC. Okay. Or for example, similarly on power management block, the budget was, sale was almost $10 billion. So certain areas are much more required in the market. Some areas are not required, but you have to create breadth and you have to create different products. As I say, if you divide the industry by applications, there is automotive, communication, computing, storage, consumer, industrial, medical are the areas which are called segments. And for example, Texas has 30,000 products, Texas Instrument. Linear has 7,500 products. National Semiconductors has 12,000 products, and Maxim has 6,500 products. They are major analog companies. Now I will show you why I did not add that word later, but that interesting part. Then what are the technologies people are working at? Very different technologies have been tried for different applications. Bipolars, many companies are working even now for amplifiers, RF blocks, regulators, power management and some discretes. Bi-CMOS or BiMOS, they are working for RF, amplifier, power management. For power, specific large power, we work on DMOS or VMOS or sometimes DEMOS, drain extended MOS for high voltage applications. Do not think high voltage means really 100 or something, 50 is very high compared to 0.8, okay. So it is very high voltage. 5 volt is also now much higher than 0.6 or 0.8. Okay, CMOS, everything, wherever they are there. Then there are technologies of very recent era, which is silicon germanium, which because Intel has popularized it for their own microprocessors. So now it has gone for every other area. RF is very strong on silicon germanium, and there are companies which are working on mixture of silicon carbide and silicon germanium called CEG carbide technologies, which is mostly used for ultra wide band, 22 gigahertz and above, okay. So which is a very great challenge right now. Why we are looking for higher frequency? Larger the bandwidth, each industry segment requires specific analog mixed signal technologies. For example, consumer requires touch screen, LED drivers, display drivers, near field communication. What is near field communication? So these are essentially required for consumer, which you want to connect your printer, you want to connect with so many sitting one common printer through Bluetooth or it can be IR Bluetooth. You for a video, audio codecs, these are consumers. Industrial, LED lighting, energy monitoring, these are same things in different format I am showing you. Automobiles, you need sensors, ADCs, line drivers, audio codecs. For computer and storage, you need HDMI, SATA, Thunderbolt, etc., some hardware and software methods. And communication, gigbits, gigb as it is called, gigabits, gigb. So 10 GB, 10G, 40G is what people are now working at Ethernets. Larger the bandwidth you provide, longer the distance your net can actually get connected without fading. Okay. So major trend in IC companies is higher integration, multiple analog function on a single chip, and of course the two people who have actually made hell of a money in last 2 years. People believe that Qualcomm has made more money, but Qualcomm has different products compared to Broadcom. Right now the leaders in pure analog RF related products, Broadcom is one and maybe Maxim is just next to it. Okay. दोनों ही कंपनी हिंदुस्तान में हैं. Okay, so what is the characteristics of analog companies? Very high profitable they should be. There should be large operating margins with them. For example, linear has 52% operating margins, analog device has 30%, maximum 26%. And the gross margins, for example, TI has 53% gross margins, National Semiconductor 68.3, linear has 77% gross margin. There is a very important word in industry which I therefore wrote fully down so that you will remember, only P you may forget. It's called price to earning ratio. How much earning you want and how much pricing you will do is a very important decision of a company, okay, and that decides whether the company will survive or will not survive, okay. If you have put very high price to get higher earning, for example ratio to what you have spent, then many lesser products will be sold. If you put very low, you may be bankrupt. So you have to be very strict on P ratios, how much company can afford to sell at what earnings they expect, because there is something minimum earnings they have to do. इस क्वार्टर में कितना लॉस हुआ आप पढ़ते हैं ना, वो क्वार्टर का प्रॉब्लम है, इसलिए दिस इज वेरी इंपॉर्टेंट. फॉर एग्जांपल लीनियर हैज 15%, एरिया हैज 14%, मैक्सिम 30. मैक्सिम इज वेरी स्ट्रॉन्ग PE people. They actually decide how much earning they should minimum and how much pricing they should do, but there are many niche products and therefore they survive. They should be resource intensive, and for example many larger companies have advantage, there are huge number of application engineers with them. For example Texas Instruments, NSC, Maxim has more I think application engineers than designers, because they should bring the business to them, okay. Sorry. So any company which has to survive, they should have diverse set of products and customers, tens and thousands of products, hundreds of package types, tens and thousands of customers of all volume levels, hundreds of distinct application in each market segment, larger product life cycle than any other IC types, very low ASPs, the profit at the start, but very high volumes. See, for example, very low profits can be as low as this may be $500,000, but you may produce a company which has 88 billion products they may actually sell over the years, okay. The most larger companies like TI, NXP, LLTC, Maxim, they do all this. The biggest advantage they hold is this: own recipes, that is own processes they have optimized processes for their own products, and they leverage their process R&D across the products. Like Intel does not give its fab to anyone, Intel manufactures its own microprocessors. Why? Because if they do so, then only they can leverage that our processor is better. Otherwise if you give it to someone else, other man will know what you are doing, and that is the major fun, okay. So all these companies, the smaller company has that disadvantage because they can't afford a fab, so they will have to go to someone, so the product का आधा release हो गया, okay. So your timing is what crucial there, you make that much product which is someone else will be interested. Cisco is interested in your product, so fine, you work on it and see to it when they pick you up. You are not interested in the end of your product either, you are just waiting when that company will pick you up, okay. That is what startup business is, okay. If you look at strategies and market force for each company, the strategy for Maxim is integration, innovation and balance. Market is automobile, HD infrastructure, energy, mobile, security, healthcare. Linear has strategy of broad based supplier quality. Market focus is communication, industrial, automobile. Xilinx has strategy of network evolution and healthcare. This company has started basically for healthcare. So Xilinx was not there in 5 years ago. It just picked up and figure out that oh, healthcare market में सब कुछ चलता है. So let's enter. So their major product right now is in healthcare. Of course they work on wireless for healthcare, that is their major interest. Okay. National strategy, broad based supplier of high performance, energy efficient, analog and mixed signal. The most important part which you can see, how much strategy is something like what are the opportunities, what is the growing appetite for analog chips in industry, consolidation restarted with the problem, this is called disruption. What has happened last year, the Texas Instruments picked up the one of the largest semiconductor company other than International Semiconductor, they just picked it up. Okay. Now they are part of Texas. Texas is a smaller company than NSC, but Texas is the owner of NSC now. Okay. Because of that, now the analog products, their own competitors, they are part of them, so they just killed the competitor, okay, by acquisition. Of course, there are still other companies, so they are not under MRTP Act, no monopoly, so they still survive, but that is the way it is. So there are potential acquisitions are now on target, and therefore there are huge threats to middle level companies. Startup is actually looking for acquisition, so for them it is great if someone actually picks up. So for example, I just word is all these big people therefore will not allow anyone else to enter the market, because that is the strategy. Just to give an idea, an iPad, there are two kinds, as I say, application specific. So for example, this application specific, some of them, for an iPad of 3G, no 3G or 3G, whichever way you buy, it's typically $225 to, this is little old price but available on net, and the analog share in that is $55, which means around 20 to 25% part of an iPad, and this is becoming so crazed to everyone that analog market will grow, continue to increase. So what is the opportunity for you all is the great opportunity for other innovative startups and smaller analog IC companies. So strategy kya hai? What is the difference you can make? Innovative designs and good analog performance, system friendliness and custom package. हर एक को अपना अलग पैकेज चाहिए, उसके लिए you should meet their applications. The focus is of course on cellular wireless, transceivers, power amplifiers, power management, chargers, supply control, LEDs, Wi-Fi, GPS, Bluetooth, near field communication devices, transceivers and controllers. $31 billion discrete से उसमें 2010 36, so 13% growth है, better to join now. 5 billion वायरलेस प्रोडक्ट 2014 में बिकेंगे और वाईफाई यदि उसका एक प्रोडक्ट होगा $3.8 billion, $10 billion का रेवेन्यू लेके आएगी. In nutshell, large and consolidated analog IC market, which is around 42 billion now and may become 74 billion soon. It's a horizontal market. That means there is no hierarchy. Everyone is on the different product, different, so they are on a horizontal plane. Different segments they are catering to. The ASP is as low as half a dollar. Many units which are very high volume, 88 billion units are made. So therefore, application specific analog is the most attractive segment for entry by innovative startups. Finally, what are the key problems one is facing, key issues, particularly wireless and analog IC market. You know, in between semiconductor market went down very heavily last 2-3 years, now it has come back. So since it is tagged with that, will analog will also have a nosedive, so that is very important issue. Will analog ICs remain viable in future, or will they be displaced by all digital? Will analog ICs remain viable? As I say, is the market becoming increasingly application specific? Will multi-market device lose their share of market? Where is the best opportunity of growth in analog ICs, whether it is in power area, signal processing area or interface area? These are the issues one has to answer. However, two things may help you. In 2016, people believe that electrical vehicles and portable medical equipment, actually that segment may grow very fast, healthcare. And second red one, I intentionally put red because I think this is the largest growth market as of now because of the younger population across India and world. Smartphone, everyone wants like this. Since you want that smartphone, there is analog 25% there, may increase even now, and if that increases, jobs in analog are going to stick for many more years. I must honestly tell you, all companies in India are looking for analog engineers because of this 25% front end. This I will show you next time, but one last slide I must show you which is interesting. These are the people whom I am acknowledging, the Razavi's book, and Razavi personally I talked to him, TI people, Cadence, the number of websites from Vlsi, Sony Corporation, Rebbe's book, Ismail Faiz's book and their work, Baker's papers, and many one of the scanless sheets which it was taken from the slideshare.net website. The last but not the least, there used to be a serial in 70s called Columbus, and the hero was a detective called Dick Tracy. I have seen many years ago in US, not in India, Dick Tracy. Now in those days the electronics was very poor, there was no wireless in reality except the huge tubes, and only there is a restricted band of 1 hertz or something where you can talk. Okay. That is what this radio ham had a problem, okay, ham radios, because they are very small bands they were given. So that detective has a watch which has a two-way communication, and he has photograph and some small things he could do, and so in that serial they showed how to use that when this was not even thought that this can happen. Okay. However, Sony as early as 2006 actually made a similar watch, okay, which can do two-way communication, it can do language translation, which is very important if you go to other countries including Japan when I go, e-secretary, camera, music and electronic memory. This is the vice president of Sony, Mr. Tsukamoto. So he was saying when he sees, if Dick Tracy would have survived and he would have seen this, he would have been turning in his grave, oh my goodness, ye to bahut hi zyada ho gaya. So this is what has happened. Even Samsung in 1999 have made a watch which can do many of the jobs which Sony is better than that in 5. Okay. Last slide but not the least, this slide I show every year, so many of you have seen it, this is just repeat for the new ones. If you are an optimist or if you are a pessimist, you can look at the same figure two ways. This is silicon wafer, compare it with sun, you are at the horizon. If you are an optimist, you say only 50% has come out, 50 yet to come, we will see it. If you are a pessimist, only 50% is here, it may also go down. Okay. So depends on the way you look at the ICs, here is for you. The last interesting slide, all of us wants to be in a good environment, enjoy our life, not doing great work. Okay. So want to be in place wherever you wish to work, in a good environment, and still be connected to the world and do every job what we would have been otherwise. That is nomadic life, connected to the world, that is what we aspire for. For you all engineers who do not want to become managers, executives might make the final decisions about, executive means managers, about what would be produced, but engineers would provide most of the ideas for the new products. After all, engineers were the people who really knew the state of the art and who were therefore the best equipped to prophesy of the changes in it. Thank you.